Hi, good morning, and welcome to the ZP Developer Zone. So every week at about 8 a.m. UK time, we do a live streaming webinar specifically for our ZP Developer Zone members, and this is that live streaming webinar. So I know it says the 7th of July, and I just noticed that, but of course today is the 8th of July. It's 8 a.m. London time, and I will go a little bit quicker because we try to keep these things fairly sharp and snappy. So let me just go down a bit now. So the first thing I want to just say is obviously every week we do this live streaming webinar. So if people have questions of a technical nature, then we post these questions in our forums and we answer them in these forums. So every week, we can discuss that. We have the ZP Academy, which provides training material. We have the ZP Developer Zone, and and if you're watching this live now, then you probably are a member of the ZP Developer Zone. We obviously offer, let's say, jobs and internships through the ZP Developer Zone. So it's probably worth saying that one of our ZP Developer Zone members is in the UK at the moment, working with us in our labs, and we offer collaboration. So I'm going to talk to a couple of ZP Developer Zone members. Now these are academic collaborations. I'm talking to them on Monday about some material, some work that we might do with them. So this live streaming webinar is driven by our forum. So if you have a technical question or a Zimmer Peacock, then we say, look, join. There's Hasim. Cool. So Hasim has come online. So Hasim is a ZP Developer Zone member. He's probably one of our, if not the first member, and he happens to be in the UK at the moment, working with us. So these forums, this webinar is driven by the forum. This week we've had 3 questions. Now, unfortunately, because of the time this morning, I'm only going to be able to answer 2 of the 3 questions, but I will answer the 3rd question next week. So one of the questions was really about oligonucleotides in the measurement of biosensors, and that one I'm actually going to have to push till next week because I read it and I thought, no, this is going to take a lot more work than just a little segment in today's meeting. So my apologies that will take more work. We will answer the question that came in about electronic tongues, and we will talk about alternatives or electrodes to something called the EDM SE5AU. So I'll talk about gold electrodes as well. And it's nice to see Shirley's here as well. So thank you, Shirley, for coming this morning. So the first thing is we've got a member of the ZP Developer Zone who's using a particular gold electrode, and they're essentially looking for alternatives on this gold electrode. Cool. Abril is here as well. So Abril is one of the longest term members of the ZP Developer Zone. And I will be speaking to Abril next week about sensors in agriculture. But so the forum question was, can we suggest some alternatives to this electrode? I think that the particular person needs these electrodes fairly quickly. So our kind of recommendation is, well, I've had a few email chats with the member, and they're essentially making an immunosensor, and they also mentioned that they've made a bit of a flow cell for these sensors. So they're making an immunosensor, which we have discussed a lot in the ZP Developer Zone, but I think they might have a bit of a flow cell as well. So there's sort of 2 things to approach here, or 2 things to address here, which is we have to talk about the immunosensor and we have to talk about the flow cell. So our recommendation at ZP is, if you're making a immunosensor and you're used to working on gold electrodes, then this electrode that we're going to suggest is actually the gold 303. So hi Anoop, thanks for joining us this morning. Now the gold 303, the reason that we recommend this electrode is, we use it a lot ourselves. So there was we had a big webinar about screen printed electrodes last week, and I kind of said, look, the reason that some of our electrodes are as good as they are at ZP is because we are the biggest consumers of these electrodes. So it's not like we're making electrodes for other people to use. We make electrodes for ourselves to use in our own programs with our clients or for ourselves. Oh, and by the way, we also sell them on our web store. So the emphasis is we make them for us, and therefore we want the quality. And by the way, then we sell them on the web store. Whereas many companies, they make them essentially just to sell them. So they're not the users of their own electrodes. And that's a difference why our quality, one of the reasons why our quality is so high. So this is just to give you a sense that if you're looking for a good quality gold electrode, and then actually this is an electrode that we use a lot. It's called the Gold 303. Here we've tested it in an immunosensor application at something like 4 concentrations. So we have 5 nanograms per milliliter, 25 nanograms per milliliter, 50 nanograms per milliliter, and 75 nanograms per milliliter. Now Hasim saw this last week and said, hi Hitcham. Hasim saw this last week and commented on this things, nice looking data. So I know I showed the data last week, but it was relevant to this week's question. And this week's question is, we're using these particular electrodes. We need an alternative. Can you suggest something? And I would suggest the Gold 303. So last week's webinar, I am repeating slightly something that this week that we did say last week, but I do recommend these Gold 303 electrodes. And I'll put a link under the video later on. I also just want to bring something back from last week as well, that if I say you how to build these kind of sensors, what we're doing is obviously we're taking these kind of gold electrodes, we're putting a sort of often a thiol layer on the gold electrodes. We're attaching the antibodies by sort of by amide coupling. Then we're often doing a sort of blocking of to stop non-specific binding. So it's a kind of it's a repetition of things that we've spoken a lot of, but I do feel like we want there's a toolkit that exists, and if you keep on doing this and only change the, let's say, the antibody, then you have a platform that will fairly well works every time. Now the way we're testing these electrodes obviously is we're testing them often with ferrocyanide at about 5 millimolar. We might do a technique like differential pulse voltammetry, and then we obviously bind some antibody and the signal will change. Sorry, bind some antigen and the signal will change, and we'll bind some antigen and the signal will change. Now we've done this work a lot internally. People like Hasim have a lot of experience in this as well, and it's a sort of workflow that works. So if you're using particular gold electrodes that you have been using, which was that ED electrode, then I would suggest the Gold 303. Why would I suggest it? Because we use it an awful lot, and I think the impedance spectroscopy data that I showed a couple of slides back shows you, well, in fact I might even go back to it just very quickly, because I think there's a couple of things that, first of all, we're getting fairly good resolution, 5 nanograms, 25 nanograms, 50 nanograms, 75 nanograms, but also, these sensors, you can see that these are 3 different sensors, but look at the repeatability between these 3 sensors. I mean, here there's actually 3 sensors. Now that speaks partly to the electrode and also partly to the skill of the guys, in our laboratories. So it is hard to repeat the skill of the guys in the laboratory, but at least if the underlying electrodes were this quality, you would not be able to get this kind of repeatability of signal. So I'll just go forward again on this a little bit and try and be efficient with our time. Now what I want to say here is, we discussed this last week, but it is unfortunately it's relevant again to this week. If you want to functionalize these electrodes, what we do is we put 3 dots on like that, and then we just blur it with the tip of the pipette, so it just becomes a coverage like that. So people they like to have circular electrodes because they can drop 1 drop on there and it spreads out like that. But we do this, we put drop, 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 and so and then we just let the 3 drops coalesce, and then we get a coverage like that, and it works pretty well, and it works very well. And if you're wondering why the architecture is unusual, Unfortunately, it was last week's webinar where we discussed that, because it's a very boring statement. I keep on saying it, but it's not because we're focused on the research. We're actually focused on people making real products from these things. And if you look at real biosensor products, they don't have circular electrodes. They often have different architectures because they're thinking about things like microfluidics and flow cells. Right, now, I said that when I was speaking with the collaborator, that they were interested in gold sensors, they were interested in immunosensors, they were also interested in flow cells a little bit. So I just want to kind of say that as long as you've got ZP electrodes and you're a member of the ZP developer zone, then we do offer essentially these free 3D printable files on the ZP developer zone. So if you take a look here, you'll find we've got something like 4 designs up there. I'm just going to focus on one of the designs today because it's how do you bring the sample to the sensor. That often people pipette, but I think this particular collaborator kind of said that they have a flow cell. And so the reason I'm sort of raising this flow cell is because obviously if this collaborator goes from one gold electrode from one manufacturer to another gold electrode from another manufacturer, then what are they going to do in terms of their flow cell? So I just want to give them a sense that actually there are other flow cell geometries, and we have, so what you need to do is go to the developer zone website, then you'll find a 3D printable file which you can download. You just contact us and ask us for 100% discount, which we will give to our ZP developer zone, so it becomes free. And then essentially you have something that is printable. So here's a picture of something that we have printed ourselves. Here's the sensor sitting in the flow channel. Now I am working at the moment with a particular collaborator or member of the ZP developer zone to reduce the volume of these 3D printable flow cells. So this one, their comment was, oh, it's a bit large. So we've given them the CAD files. So they're working on those CAD files to essentially reduce the volume of the flow cell. So if you are using ZP electrodes and you want to use them in a kind of flow configuration, then you can take a look at this downloadable 3D printable file and you can print it. And then if you're collaborating with us, we can give you the CAD and you can essentially start modifying it. So it's a side note, but the collaboration we have at the moment is we've given the PhD student the CAD file. He's going to edit it to make it sort of a smaller volume, and then he's going to give it back to us, and then we'll upload it back to the developer zone. So essentially, we give the developer zone member something, they improve it, they give it back to us, we put it back onto the ZP developer zone, and then it improves it for everyone else. So that's the nice thing about having sort of 3D printable files, because every time somebody makes an improvement on it, we can upload it and essentially benefit the community. So if you adopt our gold electrodes, then you'll also find there's a lot of sort of supporting technologies around those gold electrodes, including these printable files. And so join the ZP developer zone. If you have some ZP screen printed electrodes, then you can find that there's actually some 3D printable files that support those electrodes. Now, in terms of if you're making immunosensors, we are definitely finding that for us the best technique for interrogating the binding of analytes with things like antibodies on an immunosensor is EIS. So I unfortunately you will require an instrument. Well, I think to get the best out of immunosensor assays, you will need the EIS capability. So what we're recommending is people have an EIS capable or electrochemical impedance spectroscopy capable potentiostat. To connect to our sensor, we have a connector where we have reference working a counter, and essentially you're able to plug. We have 3mm female ports here, and so you're able to connect the potentiostat into the back of the connector. And then that sensor itself could actually be in the 3D printable cell. So the original question was, is there an alternative for a particular gold electrode, they're struggling to get hold of it. The quick answer is there's a gold 303 electrodes. Why do I recommend it? Because we use it a lot, and the EIS data I've shown you does show it. The problem is when you come off one electrode from one manufacturer onto another electrode from another manufacturer, some of your incumbent technologies like your flow cell, will no longer work. But at ZP, at least we have the developer zone where there is a flow cell that you can download the file, you can print it, and we're already working with other ZP developer zone members to modify that 3D printable flow cell. And when it's modified and improved, we'll re-upload it and essentially put a new version of it. And that's really what what we're trying to create is this kind of community where the actions or the work of one person, we can then make it available to the community so everyone benefits from it. Now this is a different question, so I'm slightly going to change track now. So I said we had 3 questions this week, and I only had time to answer 2 of them. One of them was on the gold electrode, and the other one now was another question that came in from a new member of the ZP developer zone. And they were really asking us, they want to develop an electronic tongue, and so I want to just kind of, and when I read the question that comes in, they really want to be able to detect glucose for sweetness, pH for sourness, and sodium for saltiness. So at ZP, we do have a glucose sensor. And I'll put a link down below so we can cover that sort of sweetness part. Sourness is hydrogen ions, which is really just pH. So, we have pH sensors, and we also have sodium sensors, so that we can do using electrochemistry. You can obviously measure sweetness, sourness, and saltiness by using the glucose sensor, the pH sensor, and the sodium sensor. Now somebody's trying to develop an electronic tongue. I think the first time I came across an electronic, it wasn't tongue but electronic nose, really was actually in 1997 I first came across the electronic tongue. When I first started my PhD, there was a lab sort of 3 meters from our lab where they were developing electronic noses they were developing. So I just want to kind of say there's been a long effort trying to make electronic tongues and electronic noses, and we can talk in part today why it's not been successful. But the reason I think it could be successful going forward is, in those days, the mathematics that was available to those people, they did have good maths, but there just wasn't the understanding of AI or the same number of engineers who could implement AI in those days. So I think it is a moment where actually you can probably now stand a chance of making a commercial electronic tongue or electronic nose. And I think it's really only the development of good connectivity to the cloud, and I think it's only through the essentially the number of engineers now who have AI capabilities or skills that mean that this can actually happen. So let's get to the point that they need a pH sensor and a sodium sensor, and they need a glucose sensor. But let's just talk about pH sensors, but also the same conversation is the same for sodium sensors. pH sensors and sodium sensors are ion selective electrodes, ISEs. So therefore you get, voltage is your output. So when you look at this data, which is from the ZP website, in this one you can see that if we take something like 4 of our electrodes and we measure them at pH 7, then we have a sort of voltage from 100 millivolts to 125 millivolts. Then pH 10, you can see that the voltage goes from approximately minus 25 to plus 25. Now these are all different electrodes, and then it goes up when we change the pH to pH 3.75, and then the voltage goes to here when we come back. Now the reason I show that is, and here's some other data. This is actually, this is some other data. There's two parts of the signal. There's the sort of sensitivity, which is, how much does my signal change with pH. But then there's my offset. So sensitivity on these pH sensors is quite well conserved. So that's good news. So it means that if you change a pH, the amount which each sensor changes should change accordingly. But there's this offset. What I mean by offset is we've got, in this set of data, we've got 1, 2, 3, 4 sensors, and you can see that each one has a slightly different offset. Now that offset, is fairly well conserved. That the green one is slightly higher than all the rest. The green one remains higher than all the rest. It remains higher than all the rest. It remains higher than all the rest. But this offset is not actually manufacturing reproducibility. It's just every time you use a pH sensor in the lab, you often have to do a 1 point or 2 point calibration. And that's because ion selective electrodes are very sensitive. This offset it moves around quite a lot. So that's why every time you use a sensor, or a pH sensor, you often calibrate it a few times a day. And the reason why you're calibrating it a few times a day is not because the sensitivity is changing that much. It's because the offset changes a lot. So that makes it, when you're thinking about an electronic tongue, we understand that in an electronic tongue application, it's not necessary. You're not necessarily able to actually do a calibration on it. You might just want to put the food or beverage sample onto the tongue and get the pH, and dang, you're done. But of course, most pH sensors work with it. You do a calibration and then you put the sample on there. And I sort of raise it because it's not like you can if you're developing an electronic tongue and you want to measure the sourness or something, you think, all right, I'll get a pH sensor and I put the sample onto the pH sensor and I'll get my millivolts reading, and I can turn my millivolts reading into pH, and that will be proportional to the sourness. And that's completely fine as long as all the sensors that you ever pick up all have the same offset and the same sensitivity. But the offset is a variable. And so that is, now the way we often overcome that in the lab is by doing a calibration. But in this application, you probably can't do that calibration. So I'm kind of saying you do have to be cleverer with your maths in order to not have to do that calibration. And I'm not sure that I'm going to sort of be able to give you the answer today on how to do that. My suspicion is this, that you put the sample onto the sensor, and then you watch the time course of how the pH changes and plateaus. And I suspect that time course, as you come from sample goes on, you get an initial value, and then the sensor will move and get to its new value. I imagine that the trajectory from initial sample to final sample, initial value to final value, that trajectory is indicative of the pH. And if you were using that kind of strategy, then you wouldn't have to do this single point calibration. So rather than looking at endpoint, so most pH sensors, they look at endpoint, they say, what's the final voltage? You're almost using a kinetic value, which is how is that voltage changing with time, and that is also indicative of the pH. So I'm just warning people that if you want to measure sourness, you'll need a pH sensor. We make amazing pH sensors, but all pH sensors are ion selective electrodes, and it's this offset that you have to really think about, that it's a variable in your raw signal, and you have to come up with, I would say, mathematical strategies to deal with it. The easy way of dealing with it is just to do calibration, but it's not practical in many modern applications where people just want to put a sample on and get the result. And exactly the same discussion can happen for sodium sensors. There is differences between pH and sodium, but they're both ion selective electrodes, and so the story remains the same whether you're using either electrode. Now let's talk about glucose. Glucose is I feel like I'm really boring you guys because we talk about glucose sensing a lot. Glucose sensing is the grandfather of biosensing. I think the most measured chemical parameter in the world is probably pH, but sort of true biosensors, the biggest biosensor by, say, value or volume is probably the glucose sensor. So the glucose sensor, and our ZP developers and members really know all about it at this point. It's an amperometric sensor. We apply voltage and we measure current. And this is some data off our website. And when you look at it, these are 3 different glucose sensors, all testing in parallel. And you can see that 2 of the glucose sensors have a certain sensitivity, and the third one has a slightly higher sensitivity. And so it sort of says that, you know, the glucose sensors that we provide on the website, they are good for tests. They're essentially intended to help startup companies test out ideas quite rapidly. But of course, you know, if you're trying to make something like an electronic tongue, you need a really reproducible glucose sensor probably, and you also need it to kind of work in the application of interest. You know, so it's not just, you can buy a glucose sensor and get some preliminary data, but you do have to, you know, you have to test it really in the actual matrix that you're intending to use it in. And you probably need a collaboration with companies like Zimmer and Peacock to help understand the signal, or to improve improve the analysis of the signal. Now, I'm going to say that if ion selective electrodes and amperometric enzyme electrodes, so these are new terms to you, we do have the ZP Academy. There's 2 modules on there called Introduction to Biosensors, and another one called Electrochemical Techniques for Biosensor Developers. They're both free, so I would recommend those as a bit of background reading. I'm really sorry guys, it's 8:26, so I will speak a little bit faster. Also, if you're interested in glucose sensors and understanding them a little bit deeper, then we do have a nice video in our knowledge base where we show, you know, we have a couple of videos about how to use a glucose sensor. We have a video on how to use a sodium sensor, and we also have a video on pH sensors. So do take a look at the knowledge base. So if you go to knowledge base here, then we do have another page underneath that where we actually have these videos, and I do have I have a link to that, and I'll put that under this video afterwards. Yeah, so people have been working on electronic tongues and electronic noses for a long time. I mean, I think most sort of serious commercial applications have been on the electronic nose, and it's really because, you know, gas sensors are sort of more readily available than liquid sensors. I think the only company that really has a good strong portfolio on sort of electrochemical liquid phase sensors is actually Zimmer and Peacock. You know, and but actually when you look at the gas sensing electrochemical sensors, there's a lot of companies out there. So I'd say the electronic nose has had more effort, and there's more groups have had a go at it, and there's been more companies started up. And I'm not entirely certain. So Anoop was saying sensors for bitter taste. Sensors for bitter taste, I would say, were pH sensors. But I'm just saying the electronic nose is more advanced, or there's been a lot more effort because the gas sensors are available, and then the liquids, the electronic tongue, it's harder because essentially the electrochemical sensors like saltiness, pH, sodium, pH, and glucose have not been available. It's only with company like Zimmer Peacock now that they are available, so people can start making these kind of developments. Now, if you're making an electronic tongue, you probably need to have a multiplexing system. So this is a credit card where we've actually able to place a whole row of different sensors. So you can place a sort of a pH sensor in there, a sodium sensor in there, and a glucose sensor in there. So there's no problem in bringing multiple sensors into a sample. So essentially the sample goes on here, it wicks down here by capillary fill, and then it runs onto the sensor, and as long as we've got a multiplexing electronics, we can read the electronics by making electrical contact with the backside here. And I will put a link down below just to show you that. I'm going to speak very quickly, but if I was developing a electronic tongue and I wanted to just make it for example, I just wanted to make it for saltiness, this is what I would do. So I want to make an electronic tongue for saltiness. I get a saltiness sensor. I would put the sample onto my saltiness sensor. I would put that sample into a piece of electronics that I got from Zimmer and Peacock. Now at ZP we make an app. We do this as projects. We don't have these as standard products on our website, but this is the workflow that we use a lot in people who are trying to develop diagnostics or trying to develop tests. So we have this. We often have the sensor. We obviously have the electronics, and there's an app development. And what happens is the app on the Android smartphone makes Bluetooth connection with the meter. The meter will then run the assay. So if it's a saltiness sensor, then it will essentially, you'll put the sample on the sensor. The app will tell the meter this is a sodium sensor. The meter will run a what's called a potentiometric reading. It'll read voltage. The signal comes back to the app, and now there's an upload button, and the upload button sends the data to Julie. And ZP developers, own members, they know about Julie. Julie is free. It's a cloud database system that we're developing. You can log and register for an account. It is, at this moment, Julie's free, and we're sort of developing it for the community. But eventually, it's going to become one of our sort of backbones of the business. So take the sodium sensor, put the sodium sample on there. The meter will run the potentiometric experiment. The app will allow you to connect it to the Julie database, at which point you get the raw data. Now, what will happen then is you will look at the raw data and you will use your AI capability to look at features. So you will have a signal which you can extract by looking at features. Now, if you were doing a electronic tongue application, you would take the sample and you would both taste it and test it on the electronic system. When you taste it, you would score it and say, oh, that's very salty, not very salty. So you give it a label, because what that means then is that you will have raw data and you will have the label. And then what we're doing, the workflow that we have at ZP is we say what features in the raw data are most correlated with the subjective experience that person is reporting. And so we try to make a great correlation then between taste and what the electronic signal was. And we want to have a good correlation between the two. So all the time we're improving the model of AI until we get a good correlation between the label, which is it salty, not very salty, highly salty, and the electronic signal. And that's the beauty of AI. And this is the bit that in 1997, when I was seeing people doing electronic noses, this kind of workflow just didn't exist. Literally, the cloud might have existed, but we were all just about getting Yahoo emails, let alone, this kind of level of sophistication. So I just want to sort of say electronic noses and electronic tongues are probably a technology that's possible now, and they weren't really even that possible sort of 5 years ago. I just want to talk about our experience in food sense. So the inquirer was asking, I want to develop an electronic tongue, an electronic nose. Now at Zimmer & Peacock, we've been making this food sense technology probably since about 2017. And it does really well, and it's intended to measure the hotness of chilies. So when you look at measuring the hotness of chilies in the food industry, people use HPLC, high pressure liquid chromatography. There's a lot of taste testing going on. So if somebody's making the chili product, they might actually taste it and score it that way. They might be guessing, which is that when they give like a chili score on the bottle of a chili sauce, if you actually ask them where do you get that chili score from, they've probably just tasted it, or they sort of tasted it and guessed it, but they've very rarely actually done any analytical work. But then we've developed the chili tester, the chili sensor. So what the food sensor is doing is it's replacing HPLC, which many companies can't afford anyway, with essentially, I wouldn't call it an electronic tongue. This is an analytical device that's measuring the Scoville heat units. So in chili, the experience of burn, let's say when you eat a chili, that has a unit, the SHU, the Scoville heat unit, and we have a device for measuring that. So we have a bit of experience with electronic tongues, not quite an electronic tongue, but we do have some experience around this. And I found an interesting paper, which was really, electronic tongue is really trying to match the perception that people have. So when people taste saltiness, that's a perception of saltiness. It's the way the brain is interpreting the salt. And I think, what we've discovered by reading papers and just by trying to be in this market for a little while is, for example, we can have Scoville heat units, which, increases, but the perception of burn does not just increase. People essentially become saturated. And it sort of says that, once you get beyond a certain amount of saltiness, people are not going to perceive the next level of saltiness. And that's why you can get sodium sensors from ZP and you can start this development. But the true answer around making a sensor for saltiness, you really have these kind of interesting human factors, which is, people are not that good at actually perceiving, 3 molar sodium chloride from 4 molar sodium chloride. No, their tongue's already saturated, so they're not going to perceive the hotness. Now I'm going to go a bit quicker now but what I want to say is this. In all of this research that we did around food sense, there's something I never really realized, and I want to make sure that some of you realize this. If you're making electronic tongues or electronic noses, the concentration is important. That how much pH is there is important, maybe how much sodium is there is important, how much glucose there is important. But the perception of taste is equal to concentration times the amount. And so let me give you a thought experiment. If you take a little bit of chili, just bite a tiny little bit off, you say, oh yeah, that's hot. Now if I gave you the whole chili and you put the whole amount in your mouth and you chewed it, you would really say, it's hot, and you could even be quite sick over it. So it's not enough when making a perception sensor to just know the concentration, because the human perception of at least chili hotness is based on concentration of the capsaicin and the amount that they actually got in their mouth at any one time. And that's the bit that I think we weren't aware of when we started on this work, and anyone who's starting to think about electronic tongues and electronic noses has to kind of know that the human perception of things is based on concentration, but then it's based on, if it's the nose, if I sniff a little bit, I can lightly smell it, and if I really inhale, then I really get a hit. So you have to somehow build into your system the idea of the amount of material is also proportional to the human perception of saltiness, sourness, or sweetness. And I'll put a link to a whole discussion on that on one of our websites. Right, 8:37. I went 7 minutes over. I've only answered only 2 of the 3 questions that came in this week, so I apologize for that. So we will answer the 3rd question next week. My apologies. My recommendation is the Gold 303 electrodes. If you still have more questions, post them on the forum and we will answer them. And very good luck on the electronic tongue technology. And you can have a good starting point by getting a pH sensor from ZP, for example, a sodium sensor from ZP and a glucose sensor from ZP. But just know how nuanced it is to actually make these perception sensors. But I was speaking to the collaborator and they're smart enough to know this. 8:38. I really apologize for running over, but thanks very much for coming this week, guys, and we will answer that 3rd question next week. So thank you. I apologize for the overrun, but please, if you've got any questions, guys, just put it into the chat. Put it onto the forum and I will answer it there. So I will just sign off and say hi to everyone. And Hasim, I shall speak to you later on, because he's now in our labs. All right, take care. Bye-bye.